Okay, then. So the first thing that we're going to cover is separable. Separable is going to be easiest, so we don't really need to waste a bunch of time on this. Basically, the way you're going to recognize, it is going to be some dy dx. You're going to have two functions on this side. One of them is going to be strictly in terms of x. The other one's going to be strictly in terms of y. If you can get it to separate out like that, there's a really good reason why they call it separable, because it's literally separable. And so all you're going to do is take whatever was on the y side and move it over. And then whatever's still over here on this side, we just keep it. And then simply drop integral bars, you'll finish off. And so this is a very, very straightforward procedure. The only thing you're doing is a one algebraic manipulation of your functions, and that's it. So for the example, this is going to be dy x is minus y over x squared. Okay, and so how do we want to separate this out?
Possible location.
Yeah, we can just throw the y down here. And then throw the x over here. So does this make sense? All we did was push this over here and push this down here. That's just algebra. And now we can drop integral bars. And then antiderivative of this is going to be the natural log absolute value of y. This is actually really a power rule, because 1 over x squared is x to the minus 2. So in other words, you can kind of think it's really going on. We have integral of that. So you need to be able to go between these in your head relatively easily, because this is going to be important later on. So if this is -2, but if we raise the power by 1, the new power is going to be -1. And if we're going to divide by the new power, dividing by -1, but that negative is already out here. So those are going to go away, and we're just going to be left with 1 over x, okay? And then never forget your constant. And now that we're in differential equations, this actually becomes kind of important when to remember when to put it in. Since this is just separable, and this is the last step to get to y, we don't have to overthink that. It's very straightforward. Now we exponentiate. So just drop the e's. Common mistakes that I've seen in the last few days from doing reviews with other students. They'll put the e here, and they'll put the e here, but then they will forget that this entire expression is in the exponent. So don't forget that this entire thing is in the exponent. And so now this is simply just the absolute value of y. And then e to the c, we stick that right here. And that's multiplied by e to the 1 over x. And if you need to justify this step in your head or do a few more scratch work algebra, always do it if you need to. But this is what we get. Now, how we deal with absolute value bars. So in the event, Dr. Lin said that he wasn't going to make that a big deal about it in this exam. But in the event that you do, he doesn't really tell you, and so you're like, okay, to be cautious, I'll do the absolute. It's really not that difficult. All you do is the step directly following this, stick plus or minus out in front. Because that's really what the statement is meaning, is that y could really be the negative version and it'd still pop out positive. So plus or minus e to the c, e over x. And this is actually a completely acceptable solution, because we know that that's a constant, we know that's inconstant, and then the plus or minus is just really a part of that. So if you were to write this as a final answer, there's absolutely no way he can justify taking points off. Okay, their textbooks and some things will make a substitution. They'll be like, let's define a new constant, alpha, to be plus or minus e to the c, yada, yada. It's basically just to make it look cleaner, because mathematicians are obsessed with clean looking math. But at the end of the day, on the exam, when you time pressure, don't do any of that fancy stuff. Just keep this as your final answer. Okay?
So would there ever be a time where we would have to justify simplifying the e's after we raise everything to the e?
Well, there are two, I can think of two different contexts. One, if it's an initial value problem, so you're given an initial value, I would plug that in either here or right after integrating. So
Yeah.
you wouldn't have
before
exponentiated at that point, yeah.
exponentiation.
Because then you will treat that as if it was a number.
Yeah.
So this does actually kind of matter at that point.
Yeah.
I actually recorded for some other high school students a lecture about initial value problems where you do need to worry about that. So I could also, I guess, send that link too, but it will always work out.
Yeah.
So don't overthink, wait, if I substitute here, will the algebra give me a different answer if I substitute it? No, it won't. It'll always work out if you do it correctly.
Because it's the same X right there and the same X right there. So
So separable is easy. Do not be the person who misses the gimme separable on the exam, because that's,
One second. This part right here. where you-
Oh, yeah.
You just put it up once and then.
divided by the new power.
Oh, yeah.
Yeah.
Sorry.
Actually, I'm going to take a very slight detour from the plan, because this is going to come up a lot and it's worth covering. Okay, so an exponent, if we have a polynomial. So let's just let y be x to the n power, okay? So if we have polynomials, because we do lots of derivatives of integrals with polynomials. If we were to now say, let n be negative, right? So if n's a negative number, if we were to stick it over, actually, this is a little bit too abstract. When dealing with any exponents of any nature, if you cross the line, if you move from numerator to denominator, from denominator to numerator, you're just negating the exponent. This is a very implied knowledge by the time I get to Bernoulli's especially, okay? So this has got to be really automatic. Even better, if you see more even, this has got to be really automatic too. And even further, did I just do that? I did do that, it's okay. You can do that. And even further, they're all the same, everything's the same, okay? So just know the algebra, because that really makes choosing your derivatives, choosing your integrals so much easier to be aware of, be notationally fluent. Okay, that was actually a good digression. So now the next thing we cover is the linear. And you recognize these. This is a form that should be like stamped in your memory forever, because this is a really, really important. You got a derivative of first order. You've added basically in a linear combination with some function of x multiplied by only y. This is not an exponentiated y, it's just with y. And then you only have x's over here. This is really, really important to recognize. This is linear. And so the procedure is kind of most straightforward out of the more difficult ones. All we do is we say we need to find mu such that we take e, and then the exponent of e, we find the antiderivative of whatever this p function guy was that was multiplied by our y. And then once we find this, so this is going to be something, we can simply go straight to our solution and say y is equal to 1 over mu, the integral of mu times, now we pull in this, what we know about on the other side of the equation, so that function that was only in terms of x things, dx. And that is that's the entire solution, okay? So let's see, did I make enough room to do the problem? Well, not entirely, because we haven't integrated this out. So once we do, yes, we do want to include the constant in there. But
So you only need to add a plus c after like your last integration.
Right, so the last integration that'll bring you to having no more derivatives of y.
But the one with u doesn't count, like u equals e.
Precisely, because this, at the end of the day, this is a good vocabulary term, because in case he puts this word on the test and you're like, what the heck is that? This is actually an integrating factor.
What's up? On the test, do we get to put our answers explicitly, or do we have to do it implicit?
He will say,
You won't say?
he will.
Oh, okay.
Yeah,
'Cause I was like
so-
working, and I was like, I have the answer, but I'm like, to put it in explicit was gonna be.
Explicit is y
Yeah.
equals.
Plus,
Yeah, when it looks
Yeah.
like the queens, I think it's explicit, right?
Yes.
Yeah, implicit stuff.
Explicit.
So
As long
if
as
he
there's a
says,
y, yeah.
find y, you better give him y equals something. If he doesn't say that, if he says just give an implicit solution because he's designed the problem to be that way, don't try to make it explicit. Okay, so if you see the word implicit on your problem, own it, because it's probably gonna save you a bunch of this. Yeah.
Thank you. Cool.
So integrating factor, you might recognize this because that's like the very, very last problem type we covered. But this is the easiest case of it. So let's do the example. Y dx. It's going to plus 7 over x squared plus 3. So is it separable? That's actually kind of a trick question. It actually, I'm kidding. It's not separable. Be careful. I just do want to say that when I do these examples, it's really easy to think really procedurally. And so if I do a harder example, there are actually sometimes ways you can simplify it down to be actually separable before, like just using algebra. So never assume the hardest case first, like he said. Always like try to make it easier and it'll save you time. But for the sake of example, because we're doing linear right now, we can identify a few things. So I find this very important because people like to do way too much in their head. And then guess what happens? We have to find so many mistakes that are just boneheaded. So let's identify immediately what we know we're going to use. What's P going to be? And then what's Q going to be?
squared plus 3.
It seems so simple to just farm information from the equation, but this makes it so much easier as just a general problem solving strategy. Do this, please. Because guess how many fewer points you're going to lose? Because you actually kept track of your information without believing you can remember everything all at once, always. So what we know is, what do we need to do? We need to get the integrating factor mu. And we know this is going to be the integral of px. Yeah. Okay, well, we don't have to go back to this and get confused because we've already stripped out our information. So we can just go right to it. It's x over x. Natural log. Now, again, this is just the integrating factor. We don't care about the explicit. We don't care about the most general. We just need something. So that's why we don't have to worry about including the absolute value bars here. And so that is achieved because it's really easy. It's just x. Okay. And so y is equal to what? Give the general just for the sake of review.
Okay, 1 over I, or sorry, 1 over mu, I say I. 1 over mu integral, and then I start with mu times q of x dx,
Cool.
and then I say plus c.
I would caution against putting the plus c here because that actually implies something that's incorrect mathematically. So yeah, just be careful with that.
We talk after about that.
Yes.
Okay.
No,
Sorry.
you're okay. That was my mistake. Okay. Well, we know what 1 over mu is going to be. That's just 1 over x. And we kept track of our information. So mu q is going to be what?
7/x plus 3x.
Exactly. Now, this is the part where I can see at least 75% of the class missing the last like 2 points on this part, these kinds of problems. It's because they'll put their parentheses wrong at the very end of the problem. So you get to hear it from somebody who has lost points on doing this. So what we do is we take the mean, but don't think that we just string out the integrand after here because that's wrong. Always just bracket it off immediately so you don't fall in the trap of just start listing out the antiderivative because that will be wrong. So and now we can take the antiderivative of this. So
We're missing the integrating factor.
nope, because we accounted so mu is just x.
Oh,
Sorry, what's this?
My terrible handwriting.
Yeah.
Sorry, I see it
I
now.
assumed it was dx.
I see it.
I thought I heard some say something else.
There we go. Yeah, sorry about that. As the board gets lower, I have to change the angle of my wrist and I don't always do it correctly. So then the antiderivative of 7/x is just 7. And now do we care about being exact and precise here? Yes. Okay, so. And then the derivative of this guy, or antiderivative of this guy.
We have x squared.
And now we put the constant. Okay, so this is where we put the constant. Inside the parentheses that would otherwise be distributed by this. Okay. So a lot of people will make the mistake of putting the plus c outside of the parentheses like out here. They'll do the antiderivative, they'll close off the parentheses, and then they'll throw the plus c on the complete outside. That is wrong. Because this constant is a number that would otherwise have been distributed out by the 1/x. So please, please, please get the last point on this kind of a problem. Put the parentheses all the way around the entire antiderivative. Make sure that you're doing that because otherwise he's morally obligated to count you off because it's wrong, right? And then you can influence by saying what this is why. So everything good for linear. So far, we haven't done anything absolutely mind-blowingly ingenious. For those of you who are still writing, do you need me to wait to erase? Okay, cool. I'm erasing. And as a general rule of thumb, I hear a lot of people be like, well, hopefully I'll get as much partial credit as possible. But then the strategy for doing that is always very haphazard. Things like blocking off those pieces of information, pulling it out and writing it out separately just to have it on the paper, that's a way to get partial credit. So even if you anti-differentiated it incorrectly, he'd be like, well, they knew exactly what P and Q were. So I have to give him credit for that. Even if they forgot how to do calculus 1, I can forgive that because they at least knew what they were, kind of knew what they were doing. So that's a good way to get partial credit. Write out the steps, don't do it all in your head. It'll save you a lot of heartache.
As long as you identify what you're doing right first.
Yes. So homogeneous, as Dr. Lang would say, which is both are correct because the English language is kind of correct. And then you'll know it's homogeneous if it's dy dx, if you have a derivative. If you can isolate the derivative and everything else on the other side is some function where all of the variables are basically just pairs of y/x. Everything is y/x, something y/x, y/x. So y/x becomes kind of like a variable, basically.
Is that when they're both to the power of 1 and 1 only? So y to the 1 over x to the 1?
Right, that's what it means to be y/x. Now, sometimes you'll see something that's like y squared over x squared, but that's really just saying, well, y/x as a single unit squaring that entire thing. So you'll actually see that. I think we did this in an example.
What's this symbol called?
Oh, this is just a Q.
Oh.
I chose an arbitrary. You could have done an F. You could have done an A, or whatever. Yeah, it's just to say that this is a function of something, and then what it's varying by is y over x. And like that's the variable we use. So it'll make a lot more sense when we do an example. I prefer the. Oh, I should tell you what the procedure is though. That would be kind of important. So the procedure. Note that I was kind of already, suggesting this. If we're treating y over x as like a variable, why not just do that? So let's call some variable v and make that equal to y over x. because wouldn't that be ideal if we could, then it would actually be a super easy equation because we just have one variable going on here. Now, the only problem is we haven't addressed the fact that there's still dy something over here. We need to get it in terms of v. And so I strongly recommend you just do this always. If you know it's homogeneous, you're going to write, we want to figure out what y is. And so to find y, you just do one little step, you just multiply p and x. And now that we have a description of y, we can figure out what dy dx would actually be. Bless you. Bless you. And so by the product rule, we simply take the left times the derivative of the right, and the derivative of x with respect to x is just 1. So v times 1 plus the right, so the x times the derivative of the left. Well, we need that's the derivative of x left. Okay, so if anything, for the sake of your own GPA, if anything, and you maybe don't remember the derivation, and you just resort to memorizing something, those two things. Immediately, like as soon as you know it's homogeneous, write these two things down, save yourself the heartache. You'll get partial credit for quicker identifying the procedure. And now it'll make it really easy to proceed forward in the problem. Because all we're gonna do is we're gonna say, all right, we figured out what dy dx is. So we're just gonna copy, paste, and then copy, paste into the, and then we'll have a much easier equation. So let's do an example. Is it okay if I erase this? I'm assuming y'all have written this down.
Yeah. So in the initial part of, and this might become more clear when we do our example, but how are we, like, what's a big indicator for identifying that we're gonna have to do the homogeneous?
That's a really good question, and I'll answer it as soon as I write the, so that you can see like an example of what it looks like. Because at the end of the day, it's really interesting how actually some homogeneous could technically be solved as separable ones, and so or linear, or whatever. So
Yeah.
it's really up to what you're most comfortable with, what you've practiced the most, or which you know the most of. So x squared. This is x.
Yeah, so
This is equal to y squared
basically we're
x y minus x squared. Okay, so how would you be like, oh, I just know this is homogeneous? So well, it probably won't come automatically. Just take a few seconds to think. It's obviously not separable because you've got y's and then x's and y's put together, but then they're like a linear combination. So there's no way you could like factor it in a really convenient way to be like, I can cluster all of my y's in this little section and all my x's in this little section.
If the final term had a y in it, you could, but.
Exactly.
Yeah.
But well, actually, no, because this is y squared. They'd all have to be y
Oh,
squared
you're right,
something
you're right, yeah.
to be able to separate that out.
You're right.
So the first thing that I would actually do is just keep the dy dx isolated, because as you've noticed, a lot of the things, a lot of the original recognizes come just like what happens if we isolate dy dx. So if we just divide everything through by x squared, this becomes what? Just y squared divided by x squared. And then xy, but if we divide it by x squared, what are we left with? And then x squared divided by itself is just going to be minus 1. So if this doesn't scream to you homogeneous, then now is not the time to be learning to recognize this as homogeneous the night before the exam. So anytime you get a really convenient, everything is clumped as y over x is, how remarkably convenient. Immediately write these two things down on your paper, okay? As soon as you can find the derivative, and as soon as you think you're gonna write these two things down, you're gonna be like, okay, perfect. So now I know that I can use my little handy dandy, I'll just put v's everywhere I see the y over x's. And that also immediately implies I can replace my dy dx with v plus x dv dx. Very important. This is almost as important as being able to recognize that it's y's over x's. Because now, this is actually really straightforward, just literally copying and pasting over. So this dy dx, just v plus x dv dx. So if this is y squared over x squared, But we said, okay, well, v is just whenever we have y over x, what does this become? Yeah, it's just v squared. And then plus v minus 1. And in this case, it actually happens that we can conveniently just get rid of that one of v's on the inside. So what we're really left with is x dv dx is equal to v squared minus 1. Can you identify which easier differential equation we just turned it into? Exactly. So the proof is left as an exercise for the reader.
I suck at
Welcome,
it.
welcome to what we do in Axiomatic, our 400 level math class. He's like, now that we've reduced the problem to something that we've already shown earlier that was trivial, you're all good. I'm kidding. But this is actually good practice. I would actually work on this on your own, because if I solve every single problem so that you see, you're not actually going to prepare. So do this separable on your own. There is one word of warning I will give, is that notice that you're not solving a separable equation for y. What are you actually solving for here? Do we want v or do we want y? So after you've successfully solved for v, guess what people 88% of the time forget? That you got to get it back into y and x's. Okay. So if your final answer doesn't have y's and x's, you can automatically know you should not stop working, because that's what you're trying to solve for. You're trying to solve for y's and x's. If you end up with v's and x's, that's great. Just don't forget to put the y over x back in. Okay. So you get that's a pretty straightforward separable equation. And then for the sake of time, let's move on to like the actually difficult stuff, like Bernoulli next.
Do we know like the answer for that one that you could just write out so we could know what it would look like?
Oh, well, there's so many different ways you could algebraically represent the answer. And the way I would do it requires you to do a lot more algebra than you should be doing on the exam.
Would you have to solve for dv dx to plug back into that x times dv dx answer?
So what we don't need to worry about is this. We're never going to use this piece of information again after we substitute.
Okay.
The only thing that we care about is making sure we remember to put, okay. Do you guys want me to just do this?
Yes.
Okay.
Yeah.
Let me make some screens.
That was like the one thing I was hoping to do. It's like, it's the last step. I don't know how to do
Okay.
it exactly.
So now this is a separable equation. We're gonna v squared minus 1. That's just a thing. We're gonna put it over here, and then this we're gonna put over here. So does v squared minus 1 x over x. Could you do some algebra and realize that that is a true statement? It's basically just, and then
Yeah.
so you might be like, oh my gosh, that is an integral that I don't remember how to solve. That's because you have to use partial fractions. So as an aside, okay, 1 over v squared minus 1 is equal to 1 over, how would we factor out the bottom here? Give us space.
V plus v minus 1.
Right. This is really important to be able to recognize. I guess I should point out, if you did see this, the reason you would know that this is definitely a partial fractions is because, well, you can't use sub this guy out of here. There's just no way. If you wanted to, you don't have any v's up top. This is just a differential. It's just 1. And that's not, unfortunately, not arctangent. If this was a plus, our life would be infinitely easier. We would just say, okay, great, we know what that is. That's by definition, but no, it's minus. So it's the difference of squares, factor out the partial fractions. So this is how we do partial fractions for just review's sake. We are going to add together, we split it up. So this becomes a denominator and this becomes a denominator. And then we just have a and b, or constants, right? And we're going to find what these constants are. We're essentially trying to figure out, if I were to know what these were, then I can, these are easy antiderivatives because these are just natural logs. So the strategy is simply multiply everything through by v plus 1 times v minus 1. So that'll leave you with 1 is equal to a v minus 1 plus b v plus 1. And so we just strategically choose arbitrary values of v to make either one of them disappear, and then we see what ends up happening to the other one. So if we want, let's figure out what a is. Well, we need b to disappear and go to 0. So what would we need v to be here? Well, if b is, yeah, -1. Yeah, so if we let v be -1, the b is going to go to 0, so you don't have to worry about that. So what's -1 minus 1? Yes, -2. So if we have -2a is equal to 1, what does that mean a is? Yeah, -1/2.
Yeah.
Okay, and then so to get b, we do the same exact thing. We're like, what do we need to choose here to make this go to 0? So v minus 1, to make that equal to 0, we just v need 1. So now that a is gone, what's 1 plus 1? 2b equals 1 implies 1. So these are the constants that make the partial fraction work. It was efficient. And so now we can rewrite the fraction. I gotta get more space on the side.
Why do we have a one up?
Luckily.
That's just.
Oh, this one came from here.
Okay.
So we multiplied, we multiplied this right here.
Yeah, that's what.
This equation. Multiplied both sides of this by the denominator, because then you're only left with 1. And then it happens, it crosses out, yeah. So now we can say 1 over v squared minus 1 is a, what's a?
Oh, -1/2.
Right, -1/2 over what?
V plus 1.
And then plus what's b?
1/2.
Over.
V minus 1.
Beautiful. And because now, and I would highly recommend factoring that 1/2 out, just because if you left it like that, Dr. Lang would be like, okay, it's technically right, but my eyes are vomiting. So I would just take 1/2 of 1 over v minus 1 minus 1 over v plus 1. I technically did 2 algebraic steps in there, but I hope it's fairly obvious what those 2 steps are.
Yeah.
Cool. So now this, why were we doing all of this in the first place? It's a good question to ask yourself when you do like a longer integration thing.
Figure out what I can do. Right? Or
Well,
not.
because this was disgusting.
Yeah.
This was impossible to do just by like a USAB or something simple. So we had to break it down like this. This happens to actually be really easy to integrate. So now we kind of come back, this takes us to this step, and now this is gonna take us to, we could rewrite this integral. So we have 1/2. Then 1 over v minus 1 minus 1 over v plus 1 dv. Does that make, does that now substitution make sense? We did all this work to make this look like this,
Yeah.
so that we can have something we can actually integrate. And then this is still just dx, so he's just chilling, waiting for this to cooperate. And then this is really straightforward, right? We just take 1/2, and then the natural log of the absolute value of v minus 1 over v plus 1. Is the natural log of the absolute value of x. Why am I using absolute values, and why am I suddenly being really precise and putting a c on here? No, well, because
You just finished integrating.
exactly, we have now solved for v, which is essentially the same thing as solving for y, because that's what we are substituting in.
Yeah.
So the algebra to get this one down, the first thing to recognize is this. This is a really good time to review a quick rule. If you have a constant multiplied by natural log, this becomes an exponent, it kind of hops on over it. And remember earlier, there was a really specific reason why I talked about fractional exponents.
Yeah.
Because we're allowed to do this. This 1/2 is just an exponent when you throw it up on top of this, and it's going to be square root. So that justifies this step. And note that the absolute value bars, the only reason they're there is to guarantee positivity. square roots always are positive. So that's, we don't have to say absolute value of a square root. It's just really, really unnecessary. Natural log, absolute value x plus c. Now, this would be a problem where he would definitely not ask you to solve this explicitly. If he did, that would be really funny because nobody would get it. And then but don't forget, we do still need to substitute back v. All right, so what was v? How was v originally defined? Right, but I mean.
Yeah, I know what it is. I just wanted to point out.
So the natural log of the square root y over x minus 1, y over x plus 1 equals the natural log of x values x plus 1. You could exponentiate this out and get a slightly cleaner answer, but you have 10 minutes per question. This is good. Now, if he decides to say, find the explicit solution, why? Then I give you permission to cry in the middle of the exam. I would cry if you wanted an explicit for this. It'd take another 2 minutes, precious time.
Well, if you raise them up.
Yeah, you could
and then
exponentiate.
just square both sides.
But then you'd what?
And then you have to do the rest.
Do the juggle, and then you could get it. But
That would be a.
So would it turn into?
Right. this would work. So if you wanted an implicit solution, this isn't.
Yeah, if you want an explicit solution.
Yeah, this is an implicit solution. Because we haven't isolated y, but we have eliminated all derivatives with respect to y. Yeah.
On the right, there's partial
Because
fractions.
eventually that turns into.
When do we use partial fractions?
Well,
It's like the
I'll make the
Differentiate
question
it.
very easy for you to answer. If you had to just anti-differentiate that, could you?
Does that turn into this?
So we have to find some way to make it.
differential, you can't do it, you could probably do partial fractions.
Well, yeah,
Because I
if,
thought eventually
if
that
it looks
turned
like
into-
there's something over a polynomial that you can factor, brain should think, okay, well, if this becomes impossible, I can just split it up into a partial fraction. Okay, I am going to erase,
So
is that
that's
okay?
times-
In the C, which is just. C.
Oops.
So yeah. Elect them all.
Did you sign the attendance
I
sheet?
did.
Awesome. Oh wait, did someone join? Because you can pass it over to if you haven't.
I'll be back.
Are you getting Zoom attendance next week?
No, because this is just a personal room that I'm using to record on my
Oh,
computer. For some reason, if I join his, it glitches out to the cloud or whatever, and I don't have access to that.
No one understands the cloud, don't worry.
Okay, so we've done most of the stuff. The last two are very, very closely related. So we're gonna spend a little bit more time on exact. Now, the way it was taught in lecture was really confusing, unnecessary. Okay, so am I running out of ink?
Hold on down.
Wait, I should put the name of it before I just start doing math. This is gonna be exact. And it's gonna be of the form nxy plus n y. So the only reason I put the xy's here is just as a reminder that these m and this n can be a function of two variables. So you can have like an expression with both x's and y's, and you can have an expression with both x's and y's. That's all that means. So never let notation be the reason you get intimidated from a problem. So if you ever see this with like a function and they put like two variables, no, it just means it's an expression that happens to have both, or it can have both of these variables in it, okay? So in other words, it's a more powerful, more general tool. Procedure. And this is a really, really algorithmic procedure. Your favorite. You're gonna do the very first thing you're gonna do. If you know it's exact, you're going to write down m equals, and then you put down what m equals. You're gonna say n equals, you're gonna put down what n equals. Then you're going to calculate the partial derivative with respect to y from m. So my, you're gonna write down what that is. Because you already wrote that m, so all you gotta do is look at m. And then yes,
Then X, Y is to the dy.
Yeah, which one's
thank
y?
you so much. Yes, that's, my gosh. I should have caffeinated myself after lunch. Did I do that? No. Yes, he is right. So it's dx and dy. And then n x. You don't have to do anything. We're not really doing differential equations right now. This is literally just recognize what your pieces are and then take derivatives. Write that out. Do it for the love of your test grade, okay? Just do it and you'll be much happier afterwards, okay? And then what we're gonna do, and then the next very important step is what we're gonna do is we're gonna say, okay, are these equal? Because if they're not, don't waste any time. It's not exact. Don't try to do exact on something that's not exact. Because not only are you going to be wrong, and then you just wasted 7 minutes.
So we don't need to look, because I know we also learned the integrating factor or something like this, just in case, but we probably shouldn't even waste our time looking for an integrating factor.
Well, the reason why I'm going to teach it to you in this explicit way is because it minimizes the amount of things you actually have to remember in terms of procedures. And this is the most, it's the most time-saving procedure that accounts for the possibility that you could be thrown anything. So that's why it's a little different than what was shown in class, which is just like, we know for sure we're dealing with this very specific kind of equation.
So if it's unequal, should we move on looking?
Well,
for
if it's
extra steps?
unequal, so then what we will do, and this is the next thing we'll do is then we'll do integrating. If it's not equal. But if it is equal, then we get to move on with the, yes, right?
Why is it true that he said there'd be no integrating factor?
He did not say that there would not be,
Oh, okay.
because he knew that if he said that, nobody would ever learn it. So,
I mean, I learned.
because it just is the most time consuming. This marker is also dead. I'm gonna go,
You got 4.
it's green. Sweet. And refillable? Where did you get this?
Austin gave it to me.
I need to buy me some of these. This is great. Okay, sorry.
Got a lot on Amazon.
So if yes, see, the only problem is that this is really faint. So in the recording, it won't pick up.
There's the blue one right there. The one.
Let me try the blue one.
Yeah,
There's some
I
back there as
picked
well.
it out because
There's
it's
some on that board
one
back
at
there
the
as
end.
well.
Next to your phone. That's the one I pulled out.
Oh, blue as well.
Let's see if we can read this.
Better, right?
Ooh, it's really faint. I'll just, yeah, it's worth reading.
Try this one.
Try them all.
No. Yeah, I think this one.
Give me the rest of the.
Just trying markers.
Don't work on the left as well.
Oh, there we go. Wait, someone get,
No, it doesn't work.
no, it does.
We're gonna get it on the
So if we are able to say that it is equal, we're happy. Then all we're gonna do is we're gonna say that fx is equal to m. And that fy is equal to n. So if you get something that looks exact, please just write this information out. It takes maybe a minute. Just because the nice thing is that once you do that, it's really, really obvious whether or not that you just takes half a second to verify, oh, did those end up being the same? If they didn't, we'll discuss what to do in the event that it doesn't. But if it does, because we're doing exact equations right now, simply take your fx and set that equal to m. Fy, set that equal to n. That's how you're gonna set yourself up, okay? So this is really, really important. Set yourself up. to succeed. If you have a hard time remembering these, I have a stupid mnemonic. Minx. So if you say minx, you won't accidentally do minxy. So you won't accidentally put the X here and the Y here. So if that helps at all, it's just stupid enough of a word that you're gonna go to bed like minx.
That's a name.
No, it's the name of a mammal.
I know where the match group makes, but there's an app.
Oh, okay.
Oh, me.
So now I'm going to, is it okay if I erase this?
Oh.
Minx. And also the reason why minx is important is because when we do the integrating factors, you use that same exact expression again. So you don't have to memorize something new, you just minx again.
So you identify M, then identify M, then take the derivatives of both.
Partial with y, partial with
Oh,
x.
okay.
And so that's why we have the minx thing, so that you don't accidentally take the partial with x over here, because that would be wrong. You want m to be y, you want n to be with x. Yeah, so let's do an example because it'll make longer sense. Put some math to it. Also, this is starting to get really faint.
Are you sure the blue one?
I'm really tempted to actually pause the recording to get a better marker for the people.
Okay.
Oh, if there's a purple one, that actually might work. The red won't show up. I've already tried that.
Okay.
That's really dark. That might work actually. Yeah. Thank you.
No, forward.
So let's see. X is equal to minus 6x squared y squared divided by 4x cubed y. Now you might be like, hey, yo, wait a second. I thought we were doing exact equations. Why are you giving me a dy dx in a fraction? Well, believe it or not, you can put this into differential form, right? So how would we do that? We'd start by cross multiplying, right? So at least get something with dy times something and dx times something. So if I were to cross multiply here, take this is going to be pushed up here, and then take this and then just stick right here. So we would have 4x cubed y dy equals negative 6x squared y squared dx. Now, this isn't quite though in the form of an exact equation, right? Because it needs to be m, like expression dx plus something dx. So we need this on this side. So all we got to do is just add this over here. No big deal. So we have 6x squared. Actually, I don't need it in parentheses, really. It's kind of unnecessary. We could just say 6x squared y squared dx plus 4x cubed y is equal to 0. Oh my gosh. There's an m and there's an n. So we can. So what are we gonna write down? Which is, it's gonna be 6x.
Oh,
this
sorry,
one right here.
sorry.
Yep, you're good. So 6x squared y squared. Okay, what's the next thing we want to put down? And
4x cubed y.
exactly. Okay, so how do we remember which partial to take with which? Exactly. So that means m with respect to which variable? Y. Okay, well, let's do that one first, right? We know what's next, but then since we already have m, we already wrote it out here. What's m? But we differentiate with only respect to y.
Sorry, 12x squared y.
Right, so x is just a constant, we treat it like it's a number, so y squared, the 2 comes down, multiplies with the 6. So with 12, the x squared, and then we reduce the y power by 1, so 12x squared y. And then what's the last piece of information we're gonna write down? Sure.
The same thing.
Yeah, fine.
We don't know that. Well, yes, it is, that is how it's gonna happen,
I
but
mean,
for the sake
I
of.
wrote it down. I
Right.
know it is. I'll say it explicitly. though.
So, but if this is my to finish mix, what do we have to put here?
Oh,
And x. So, and what is nx? And from here,
x to the third goes to 12x squared y.
12x squared.
We're respect.
So does this satisfy smiley face?
That's pretty good.
Yes, because these are equal. And so what's great about this strategy is that you have actually justified exactness without having to do an additional step. Because if you've written on your paper, you've computed both of these and then they're the same, you can't lose points for not justifying that. So that's why this is just a really compact way to do this. Okay, so then we've shown that that's good. And so that last thing we need to do, we said fx was what? Fx was m. And then we can just substitute m real quick so that we know what's going on. So that's 6x squared y squared. And then what's the second thing we write down? What is fy going to be? And so n is just 4x cubed. Do you see why I really encourage this step? Because it just makes life 3 million times easier. Okay, so
What's the detail of that one? Yeah.
yeah, and then this. So this is what a lot of, okay, I'm gonna call it, this is gonna knock a lot of people's points down because they're gonna forget to put the fx with the m and then the fy with the n. So that's why you're here. That's why you're studying and you're reviewing so that you won't make that stupid mistake on the exam. Okay, so fx, m, fy, n. Do you guys have the upper stuff here so I can erase like the top two?
I have a question regarding the upper stuff.
Okay.
Is fx regards to dx for, like, is there a relationship between dx and fx?
Oh, I should clarify. The actual solution to the exact equation will always be f equals c. This is the answer. If it's an exact equation, that's the answer right there. So that actually leads me to a more exam style tip. If you were able to recognize it's exact, or something happened to a one, maybe you ran out of time, or you got into an integral that was confused, you didn't know how to do it, just put this somewhere on your paper. Because this at least shows you that you knew exactly what that solution should have been at the end. You take whatever was f, and then it's just set it equal to c. So this is the end goal. We're going to take these two pieces of information to work now to getting what our f is, and then we're done. So now, is it okay if I erase?
It's okay. I don't care anymore.
Just like, I'm just gonna erase like the first the first 3 lines. So I'll just put this here, this is the end. So we are equipped now with what we these things. So we have fx equals this. So in this case, these are both equally easy to integrate. So let's just go with this one. We're gonna say we can now solve for f, because if you took the derivative of function and then you just integrate it, you get back to the function, right? So that's the motivation for the strategy. If we were to just integrate fx with respect to dx, this is f, right? We get back to f. So all we gotta do is plug in what fx is. Well, we know that fx was m, and then because we had taken this information, now we know that's just 6x squared y squared dx. And so what is this antiderivative? No, it's with respect to x. As soon as you see that, anything else that's not an x, just a constant.
So you could take 6y squared out of that integral if you wanted.
Yeah, you really could, honestly. If it helps,
Yeah.
do it. Because what would then all be that's left? That you're actually integrating, yeah, it's x squared. So what then is f?
That's the 3y squared x cubed,
Well,
or 2y squared. that right.
Yes.
I said that wrong.
You got it.
And because I have OCD, I'm gonna put the X first.
Me too, I was
I feel that.
tripping.
Just like if the alphabet wasn't ordered, I wouldn't care, but it is. Okay, yeah, but notice that if we were to take actually, and what are we missing now right now? Because we did an integral. Well, you have the right concept. We do need we need a constant, but because we're doing partials, that constant ends up being anything that was a y. Because note that if this was a y, and if you took the derivative with only respect to x, we would treat that like a constant and just slash it out as a 0. So that's why instead of just being like a constant, like a number, like a c, just like 4 or pi or 32, it could be maybe like y squared. Because if we were to then differentiate this with respect to x, this just goes, all of that will go away to 0. And then we'll get exactly back to where we were starting.
Okay.
Yeah. So always have a function constant, especially if you have the partial derivative stuff. And so once we get to here, note that we used the fx. What piece of information here did we not use yet? Fy. We haven't used this information. So let's take the derivative of this with respect to y now, because that's what we still need. So now if we were to differentiate this expression with respect to y, what does this turn into?
2/3.
So x has become constant. So the only thing we care about is the y changing. So it'd be drop this power down, so it's 4. 2 times this 2. This is just constant. And then reduce the power of y by 1. So it's just y. And then whatever this was, we just call that c prime. Yep.
Oh, just, so in that first f, so f is equal to x cubed y squared.
Yes.
So that, the y figure right there, so right after the plus sign.
Hmm?
I'm sorry, that when we were doing it, he used like g prime y, is that what?
I keep realizing that y'all love English alphabet. I'm sorry. I'm using
I just
Greek
wanted to make
letters.
Sure, that was.
Yeah.
Okay.
Okay. It's a function with respect to y. I could have done house with a smiley face of y. Okay. This is just some sort of function in terms of y.
You allowed that in the exam?
He would. I've been this close. If I lose more sleep between now and then, I will do it. So yes, to answer your question, this is the logical, mathematical, symbolic equivalence of the G that you are so familiar and beloved. Okay. So if you're more comfortable with G, please use it. This is so automatic that I actually didn't think about that. I just put it on the board. So yes, sorry, this is the function.
What? Why is there a y again? Like at the end of the, like,
Oh, this step?
there's a y up there and there's also a y here. What's going on?
So this is what happened when we integrated it with only respect to the x's. So now we've only done one kind of half of it. We've only done the x's, and that gave us this step. And so we recognize, okay, well, we've only done the x's, but now we take care of the y's. And so then you enter into that's the last part, which we're saying, let's take care of the y's, which we haven't done yet. And we do that by differentiating this with respect to y specific.
Yeah, but what is that? Just the form of like, you know what I'm talking like this was.
Oh, okay.
Yeah.
So if this is a function,
Yeah.
and if it's with respect to y, if we differentiate with respect to y, then this just becomes the derivative of this function. So that prime means
Oh,
derivative.
you're just saying okay.
Yeah.
Sorry.
Let me adjust this chord. Okay, so guess what? We did right. We wrote down what fy was. So all we got to do is, what does this end up being? What did we show it's supposed to end up being? There we go. So now we can actually solve what this mystery y function was. In this case, it happens to conveniently cancel. Doesn't always do that.
What's the where's the 4x if there's y coming from on the right side? But they're coming.
Yep. So that was kind of like we said this. We dealt with the x half of the problem. We got back. But now we needed to take care of the y side of the problem. And then that's when we use this piece of information. So if that makes sense. Cool. And then we can do another, after the report, we can do more exacts. So this implies that this is really just 0, right? Which is great because that's just nothing. So we don't even have, this goes away to 0. So,
You said prime equals 0?
oh yeah, well, f prime is equal to 0, but if the derivative, if you integrated 0, you just get 0, right? So yeah, the function prime is 0, so that implies that just the original function is 0. Terrifying point. So the question is, and the hardest part about exacts is not circling the wrong final answer. Okay, so remember that the end goal was getting f equals c.
C can be negative. C can be negative.
C is the arbitrary constant.
Yeah.
Yeah, so it could be anything. But if we're finding like the general solution, so in this case, f is 2x cubed y squared plus this. In this case, it happens to be 0. So I'm not gonna waste your time and say plus 0, because that's almost insulting. And then equals c, never forget that part. This is what you want to box as the solution. F equals c.
Is it okay to write F? Is that C? I have no idea.
You mean like,
No.
oh,
Like an F instead of a C.
Probably not.
well,
I wouldn't, but like maybe I forget, you know.
that's why you write this on your paper, because then you know that at the end of the day, you're just gonna take whatever you found for f and then send it equal to c.
The point of doing that extra step was just to verify that it goes to 0.
Yeah, the point of doing this was just to figure out, to make sure that what phi y was. I'll try to find a problem where phi, like this actually is a function with y's in it that
Yeah.
you do have to account for.
Yeah, because I was like, so why did we have to?
Right. In this is kind of a bad example because people are like, oh, it's always gonna go to 0. So let's never double check what this is gonna be. It often actually is something. But the only thing, it's not any conceptually different. All you would do is simply take, so suppose it was an actual function, like sine y. Then all you do is put it there, copy paste, same difference. Yeah. Cool. Excellent. We are on the last one. And not only is it good that it's the last one, but it's so similar. It's so similar. So it will be very easy to pick up.
How good at math do you have to be to get an entire equation set named after?
You have to be really good at math.
Is there a chance we're gonna be having like a Caleb style differential equation?
I am an educator first, not an academic. So I would prioritize helping others learn what I have learned instead of coming up with arbitrary stuff to hope that one day I'm famous. Because here, think about it like this. If I get an equation named after me, that's great. Then that gets abused by scientists for the remainder of human history. Or if I'm a teacher and then I teach across my entire life, say there's only like 50 students.
You get to abuse other people's equations.
Forever. And that's an exponential growth of influence versus one equation. So I don't know. That's how I see it.
Caleb logic is interesting.
Yeah, Trey?
Are we gonna be covering Bernoulli's?
We did.
Did we do?
We did it.
I was gonna say, wait, Bernoulli's are
You,
similar
you
to.
literally just said, now we're gonna do Bernoulli's, it's so similar. Proceeds to write.
I don't think so.
integrating factor.
Well, that's my bad.
Either one.
Okay, we're gonna do integrating factors because it's very similar to exact. And okay, yeah, so I'll put here like similar to exact.
From on the test.
This is the one where I can totally see him putting it on here just for me to snipe me, try to like see if I'm slacking.
Number 6.
But know how to do it because it's something like, but I genuinely did forget to do the Bernoulli, so we will go back and do that. Yeah, my bad. The same exact way to recognize it's gonna be m something dx and blah 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 dy equals 0. So shocker, procedure. Whatever those four things we wanted to know. M and minx. That is exactly the same. Which makes this strategy neutral because you're still technically saving time because if this was exact, you're helping yourself get to the solution, you're closer to the solution. So again, we double check. And now we're taking into account that it's not equal. So we're dealing with the not equal case. So what if we show that it's actually not? Well, the first thing we do is we panic and scream in the streets and wail and mourn from the rooftops, and then we realize, okay.
That's how we know are you.
There are two formulas that I'm not a fan of just giving people formulas. But given that it's Thursday night and the exam is in less than 24 hours, I'm morally obligated to help you maximize your grade. So we're gonna do this. For P, so what we're trying to do is we're trying to find a little P of X. And what we do is we say, we take minx, but it's gonna look like this. My minus nx in the numerator. And then for the denominator, it's n. This is how we define P of X. And then similarly, if this doesn't end up working, so the idea is if we want this to be a function that only has x's in it. So if you compute mi minus nx over n and you have things with y's and x's, stop right, just move on to the next one, okay? Because that's not going to work for you. Then you check qy, little qy. It has a very similar structure. You just flip the top around so that you do the nx first, and then flip the m at the n to an m. Now, he promised to the class, to my disappointment, that he would not ever give you a problem where both of these fail. There is a strategy that's actually interesting if you're a maths person, where if both of these fail, and then you have to use your actual intelligence to solve the problem. And there's something different for that. But for this exam, he promised there would be no case, he would never give a problem. He might for the final. That would be really funny. But no, so but that both of these fail. So one of them will work. Okay. This looks like a lot of information. It's really easy. P, minx over n. And notice that this is always different than this. So if you can't remember if the denominator is the m or the n, just look at the leading term. It's not going to be the same.
Well, it's always the last.
That's another good way. That's a good way to do it.
The way I think about it is I put my hand up like this, and then if I got my M here and my M here, good, right?
Oh,
Right hand rule.
so what we're going to do with this information, this is how we're going to get our integrating factor. And this is really, really cool because earlier the integrating, remember, there was a reason why we called with the linear equations, why why we called this was an integrating factor. This should look familiar because we did this with linears. Same exact thing. We're doing nothing mathematically different. So if this ends up working, if this is the one that checks out, you can get a P of X where that's only in terms of x's, then just do the linear strategy. You can get your integrating factor mu, and it's just going to be exactly the same. It's just literally, it's the same exact formula. E integral of that P x dx. And so by shocking logic, oops, we do mu, but this in this time is with respect to y instead of x, which is fine, it's just a variable, right? Can anyone conjecture what the mysterious formula is gonna be? Exactly. So, well, and the function, like instead of P is Q.
Whatever.
Yeah, so Q, Y, Y. Mr. Whitaker. So this, the end goal, okay, what we're trying to do is we're trying to find the mu. Because we are guaranteed that if we take that mu and then multiply it by n, and n, multiply it through everything, it will be exact. And that means I'm gonna give you the shortcut of the century because y'all are engineers. So we say fx, normally we would say this is what, like if it was exact what we would put. Yeah, we would put m. But now, because we have this integrating factor, just throw on the mu. And so then what do you think Fy is going to be? Well, normally, if it was just exact, what would we put here? We would just put n, but then since we're multiplying everything, we just do that. Yes, that's a product. And then the solution is just exactly the same as exact. So really, this method is just saying, do this one detour of a step, and then it's precisely back to something that you already know how to solve. That makes sense?
I feel like the hardest part is getting to the my.
Yes. Here's a common mistake that I 150% will guarantee will happen to people on this who did this hard. They'll find P, they'll freak out because they're so excited that they actually remembered the formula, and then they'll say that P is the integrating factor. Then they'll multiply n by P and n by P. Yeah, that's really not going to help them. You gotta find the actual integrating factor by putting it out. So find your P, find your Q, but don't forget that that's actually just the step to get your actual integrating factor. So this is not the integrating factor, but we use that information to actually get our integrating factor. That's the only place where I could see people definitely getting sloppy, getting lazy, and then just get very confused very quickly. So let's do a problem, shall we? Are we good if I erase? This is going to be a good cumulative problem. Y'all are going to go back to Bernoulli's and be like, oh, this is chill, which is maybe a good thing because now you're not afraid of death or anything now. Okay, so 3x squared y.
I still might survive.
What if I sit in the back? It's 2x cubed.
Life finds a way.
Life finds a way. That movie's coming out.
Really?
What is the new Jurassic World?
I'm honestly very excited about that.
You know what? Good movie,
Trailer's
yeah.
out. Trailer for that one's out if y'all want to look at it. Cool.
I mean, after
Yeah.
It's just gonna be interesting how they fixed the mess they made in the previous movie. But anyway, so what's the first piece of information, or well, it's technically 4 pieces of information, but what are we trying to get out of here first? Because who knows, I might be pranking you. This might actually be exact. Okay, you never know. That's the point of the exam. You don't know what kind of equation this is until you picked around at it. So what is m?
left side. 3x.
Yeah, sorry, it's hard for you to see 3x squared y. And so what's the next piece of information?
N is equal to 2x to the 3rd. And we want Minx. Minx is our friend, or my friend.
So but then how do we use that to actually finish this out?
Oh, you want to take the particular with respect to y for m.
Exactly. So what's my?
I'm just gonna make two, because it's fifth there.
Oh,
Six
sorry,
squared,
yeah.
yeah.
I missed that.
Let's not forget.
So, someone was joking around earlier, oh, just write down 3x squared. Well, turns out if you did that, you would get this question wrong. So, what do we notice about 3x squared and 6x squared? Are they equal to each other?
Yes.
No.
Problem solved. Therefore, the answer is 17. We're done. So if you circle this with confidence, you will get 100% on
Is
the
it
exam.
confidence that matters most?
Okay, anyways, so these are not equal. So what are the two things that we have two options we could pull from, right? We could try to do the one where it's P is minx over N, or we could try to do Y, but there's no reason to do it with respect to Y because there ain't even Y's. So we know kind of that it's going to be some sort of a P.
Would Y give you the trivial solution?
Exactly, because it would just be 0, 0, 0, 0. So it's meaningless. So I'll assume you can plug and chug and tell me what this reduces to. So my is what? What's nx? Okay, so minus nx, so minus 6x squared, divided by what? Huh? So then the numerator just reduces to what? If we have 3x squared minus 6x squared, it's minus 3x squared divided by and then 2x cubed, which I hope it's fairly obvious that this is negative 3/2 x to the minus 1, or just over x.
I would put that. Just saying.
So is this our integrating factor?
No, we gotta do our, is it mu substitution you call it? So
Yeah, well, so think linear at this point. So this is P, this is the P. And in linear, what we would say is mu is e to the integral of P. This is the integrating factor.
Right, we stop.
So don't stop here. Plug this now into what we know is the formula already. This is from earlier. This is the linear. Plug it into here. So we're gonna have e integral of really so minus 3/2 over x dx, which is kind of cute because it's just negative 3/2 natural log x. Why do I not care about absolute value bars here? Integrating factor. So we just need something that works. And then, well, I kind of want this to look cleaner. So here's where people freak out. They think, oh, notation, fractions, negative numbers, impossible. It's not. Just take this, make it the exponent. Never be intimidated by notation. Because now this is super easy what this is. It's just this is x minus half. So if you ever get this, please don't be the person who says that this is e to the minus 3/2 times x. There would have to be a plus sign in between here for that to work. Okay. Multiplication. If it's a constant multiplied by the natural log, just put it in as an exponent, get rid of the logs, and then you get something. You get a polynomial. So, are we done?
No, it's just alright.
Right, this is just ready. What do we do with mu? Okay, so that's where we come to the next key equation. We are now turning this into an exact equation. We're turning it precisely into something that we've already discussed how to work on. So fx is what? It's m, but then we now multiplied it through by mu. So that is this times this. So I'll write it out so you can see. So I take m and I say 3x squared y, and then I take mu and then I multiply it. And then when I simplify that, you can add the exponents here because the x's are multiplied. So 2 minus 3/2 is just 1/2. So it's 3x to the 1/2 y. That's what we end up with fx. And then what, but do we just stop with fx?
Yes.
See, you can't do that to me on a review because that could genuinely be a concern.
Don't stop, I'm making.
Don't stop believing. I love listening to that song when I'm doing linear algebra homework. Because I'm believing that there will be a better day when I can go back to more abstract things instead of crunching numbers. Okay, so sorry, Fy is equal to what? Excellent. Okay, and so we know that n, we just, when in doubt, increment the steps. Again, people do way too much in their head because for absolutely no reason, and then they mess up. So it's 2x cubed times x minus 3/2. What's 3 minus 1.5? Right, so it's just x to the 3/2 positive 2x. So do you see how we've turned the entire problem? Now just do an exact equation. Hey, what's up? Yes.
Just don't use
Just don't eat next to the computer because then the poor virtual students will have to hear Nate chewing.
I don't worry, nobody.
So is this pretty clear how we got to here?
plug and go.
Right, we are literally doing we're doing tons of plug and chug honestly. So this is actually now, if you notice, we kind of teleported to this step in as if it were just exact, right? We have our two pieces of information. So what I'm going to do now is I'm going to clear some space. I want to keep this information up. No, wait. I'm going to get rid of this information because we don't need this anymore. And I'm going to condense the information down so that we know what's up. So I'm going to stick over here. So I'm going to add that f x is equal to 3x halves y, and that fy is equal to 2x. Okay, there we go. Now I can just erase the bottom part and so this is now transformed into an exact equation. We have an fx and an fy. This one is going to be easier to integrate. Do you agree? And if you're like, how do they know that? Would you like to integrate that with respect to x? Or this, which has no y terms in it, then just plop a y on it, right? So if you want to, you could do it this way. You're going to get the same exact final answer, but I am lazy and I like easiness, so I always take advantage of that. So we start with the fy. So we're going to get back to, because remember, what is end goal? Yeah, if you said c equals f, you said something equivalent. Okay, so this, any form of that. So that's the end goal, which means we're trying to find a full expression for f. So we integrate because we decided this was going to be easier. We're going to start by doing the y half of things first. Okay? And since you are clearly so bored, Anna, because you know everything, what do we put into this integrand?
Sorry, I was.
So f is equal to, so it's fy, we're doing the y half first because this will be easier to integrate with respect to y. So what's the integrand and what's the differential? 3/2, yes. dx or dy. So what does that give us?
Well, if we just add 1 to the exponent and divide it by
To G1.
to do 1. So we just add a y.
Is that all?
G.
G.
Plus a function in terms of x's.
We're in Greek at this now, man.
That'd be plus a little house with minus.
Isn't that C?
Oh yeah, shoot, we got to do the house.
I prefer house.
Should we do a smiley face?
Yeah.
If I can say it out
He's
loud, I
happy
like
like
it.
this.
I like this.
Hey, yo, this is actually gonna fix my mental health. Okay, so we did the y side of things. Okay, so we did the y side. We have to have both, so now we gotta do the x side of things. So let's take the partial x with what we got. So what would that be?
So since we. So we, one y. We bring the exponent to the front
Right, we just take this guy, plop 3/2 times 2 is just,
and subtract 2/2 from that.
and then what about Smiley?
Prime of Smiley.
He's in his prime. Excellent. But what we haven't used what piece of information? Why did we do this?
Because we need to put it now in terms of, we know what f of x equals.
Right, this guy now, we use this information right here. So it's 3x 1/2 y.
We use that to solve for Smiley prime,
Yes.
which
Okay.
is
Unfortunately, because I know you earlier asked, does it always go to 0? I don't know why I chose this example.
I can confirm
Because
it's not always go to 0.
In this case, it does again, but we can actually do that problem if you want later, because then it'll be good. But yes, Smiley prime equals 0, which implies that Smiley is just 0. Again, disclaimer, this doesn't always happen. So don't believe it always happens this way.
Wait, no.
But I mean, it doesn't actually make that much of a difference because you're literally just copying and pasting this into where Smiley shows up over here. So f, this was the expression for f, right? This was f. So we're almost done. All we got to do is say 2x 3/2 y plus whatever this was a function of x. If it would have been something, you would put just tack it on, but it's 0. And then equal to c. Now, because I'm a sucker for, if you have an easy y, just grab the explicit solution, right? Y is equal to c over 2x. Are we happy?
That's good enough.
Do the cows roll on green pastures?
Yes.
Do the sheep bathe in the sun?
What's the
Oh,
final
data.
answer? It's the.
Yes. So if you would have wrote this down, this is equally correct. I just did this because I could not contain the urge to make it pretty.
So for every time we integrate there, we can effectively kind of ignore the constant because we're just saying.
Because that's already accounted for. So that's what makes the strategy unique. We've already accounted for it at the very, very
So we
end.
can kind of describe it.
Exactly.
Yeah.
So this is the hardest, okay, if like this would be the hardest problem on the exam, something like that. And that wasn't really that bad. As long as you just follow the steps, write your work down, don't do things in your head, don't make mental skips, don't make mental shortcuts. And you'll be fine. Okay? So we're gonna now go to something that's gonna feel super easy now. This is Bernoulli.
We're gonna be covering Euler's stuff, right? I don't.
We can cover an example of Euler's.
I don't. Gracias.
Well, it's gonna be on the exam.
Oh, yeah,
Yes.
Euler's stuff.
He confirmed that there will be a two-step Euler on the exam.
I'm
sure.
hoping it's the same.
Watch it be, yeah, d by dx is x plus 1.
Oh, no, not an easy one. I'm hoping the proved one will be using the same numbers.
Oh, okay.
You know, because they relate.
So we recognize a Bernoulli and it's similar to the linear because it's just dy dx plus p of x y. Notice that this side of the equation is exactly the same as the linear. So that's good. And then it's almost the same on this side because we have something with respect to x, but now we just add a y with an exponent. And then specifically, we have n is not equal to either 0 or 1 in this case. Because if it was, I mean, no big deal, right? You would just make it their life easy for yourself and then solve a simpler version of the differential. But we're worrying about what happens if it's like different, you have to deal with a strange exponent. So the procedure or favorite, it's going to be a kind of substitution. It's a type of substitution. We're going to do a very specific one. So this is what you want to memorize. If you think Bernoulli, your brain should immediately shoot to this. V equals y to the 1 minus n. This is remarkably important because this is the result that it took a really brilliant mathematician to figure out that this actually works. So remember it, take advantage of a very powerful result. Because all you're going to do is you're going to take the n and put it into there. Oh, so this is just like what happens if this exponent isn't 0, 1. Because if this was just 0, well, this is just 1. Like that wouldn't even exist. So if n was equal to 0, we actually just have a linear. So then there's no need to make it special. And then if it was just 1, well, we just divide both sides by y, right? It's actually separable. So again,
that's just one of the parameters we look for.
right. So this is letting you know that there is a way to solve these kinds of equations in the event that this exponent is something nasty. Yeah. And this is the key right here. So Bernoulli, my brain immediately thinks of this because this is the only way you can actually solve this problem. So the substitution you want to make is you're going to take the derivative of v with respect to x. So you're differentiating both sides really with respect to x. So dv dx, and then whatever this happens to be. Like x. Don't freak out. No, trust me, when you actually do an actual example, it does not look this ugly. It looks really nice. Okay. What we're going to do is we then strategically multiply the original equation by whatever ends up coming in here. Because if we do that, then we can just copy paste the dv dx in there. So I'm not going to waste your time with the general form because it's actually more confusing than just doing an example. See, I'm like artificial intelligence program learning how you guys learn very slowly, trying to optimize it.
Skilled artificial intelligence in the future.
Do I think what?
You think when we compete against more skilled artificial intelligence in the future?
I don't think I would be even a contention. That's the main thing.
Oh.
I would, because computers can do a lot more than a human brain can.
Yeah, you can hook up multiple computers together. We cannot hook up.
So dy dx is equal to, I'm trying to, when I was coming up with examples, I was really trying to give them to you in the form that is going to be familiar on the exam. Because he said they were going to look like dy dx equals something, something, something.
That's true for example.
Yes. So 2y plus xy cubed. As soon as you see a y multiplied by like this, now you have like an x on here. Think Bernoulli. It might not be, but it's most likely gonna be a Bernoulli.
As soon as you see a y multiplied.
Well, yeah, like if it's an exponent on the y,
Okay.
because that's precisely why Bernoulli exists as a strategy. So just be careful. We double check that. Is it possible? Is there a little cheat factorization we could do to make it separable? No. Okay. So we've got to now do it with the Bernoulli. So we want to get it into the form though. We don't want to just start Bernoulli right now because this is not in that form, right? It's got to be the derivative plus the p of x. So we have 2y equals xy cubed. Very similar to how we did it in linear. Just take inventory of what the anatomy of the equation. You will save yourself so many points. What's p? And what's q? Okay, why did I do that step? We don't even need to do that, my bad. I got very distracted by a thought that I had. We're doing Bernoulli. So the information, this is the information we're taking. Sorry, so if it was linear, you would take P and Q, but since it's Bernoulli, we're taking just the N. So N is what? Which means our fancy little substitution is gonna be what?
V will equal y to
Y squared. Or -2.
Right. Because what's 1 minus 3? 18, somewhere on their ballpark. Okay, so this is the substitution we're gonna make. Now we need to immediately write down this. So if we were to differentiate this using the chain rule, we just throw down the exponent and then reduce the power by 1. But then tack on dy dx, and we're done. This right here. Notice that if we were able to multiply through this entire equation by this, we would have something that we could then just throw the dv dx in for, right? So the dy dx by itself is, but if we add this in front of this, if you can imagine it being right here, we could just replace this entire expression with dv dx. So that's the motivation, okay? So multiply through everything here. So we're gonna have minus 2y minus 3 dy dx. Bingo, beautiful. Now we multiply this by this because we're just multiplying through one at a time. So minus 3 times minus 2 is plus 4. And then y times y minus 3 is just y minus 2. Conveniently, this middle term right here will always be something in terms of this. And then up here, well, the x is going to stay there. We're going to have minus 2x, and then the y3, y minus 3 goes away. And that will always happen too, again. So this will always be in terms of v, and this will always be in terms of just the x, because now we can substitute. So this looks gross, but notice that that's precisely why we strategically multiply like that. So this is just dv dx. Does that make sense? Because honestly, if you can understand this, this is the hardest part of Bernoulli, is just remembering that this is what we're substituting in. So if this is good, you're golden. Make sense? And if you're wondering where this v came from, remember, we have two, it's always a pair of substitutions for the variables and then for the derivatives of those variables.
So is that second term always going to become b?
It will always be something in terms of v. So it'll always be function of x times v, function of x times v.
If you did it right.
Yes, if you didn't, then yeah, do it again, right?
I was staring at it and just confused myself. Where did we see that v is y?
Oh, yeah. So let's see, so that you can find it in your notes to make it see. So right here.
Oh, up there.
So we plugged in this guy. And that's what we said.
Minus one
So
minus
I'll write it right here so you can have it in there. Y 1 minus n, but because n equals 3, y 1 minus 3. So that's what I wrote down.
Okay, thanks,
Yeah.
thanks.
No problem. Who recognizes this? Well, that person who is someone earlier would have to be very correct. So now we want to take inventory. So this is linear. So what's P? Notice that we're immediately taking inventory of our stuff. Nice and easy. And what's Q? Yep, just minus 2. Okay, quick question. When we solve this linear equation, are we solving the problem originally asked? No. We're solving the question that we just created for ourselves because the original question was too hard for our brains to comprehend. So now we're going to be solving for v. And then we want to resubstitute at the very end. Okay. So in this case, mu is just what, right? This is, again, we're repeating stuff at this point.
E to the power of e to the power of an integral of p.
So e to the integral, and we wrote down what p is so that we don't get confused. It's just 4 dx, meaning that we just have e to the 4x. Beautiful. Again, no constant needed because we just need something that works, and this is the easiest one that does work. Okay. Now, am I going to put y or v here? Yes, v is equal to 1 over mu. That's the integral of what? What's in this integrand? Yep, mu q dx. If you put a y here, and Dr. Ling is grading this exam, he will probably start laughing. Okay, so don't give him the satisfaction of being like stupid. No, so just put the v right here because you're solving a linear equation. Okay, this is really important. I'm gonna call it. He's gonna have to dock at least 4 people in the exam for putting y here. Guarantee it. Because it's really, really easy in the heat of the moment, time pressure, exam conditions, to just make a silly mistake like that. So what kind of a star is that?
A unique one.
Maybe 7 point.
Make sure when you come down to this part, you're very, very, very conscious of what it's supposed to be. Okay, so now let's solve for v. Yes, but it's an easy tic-tac-toe. Okay, so 1 over mu is just e to the minus 4x. Do we agree that when you move an exponent across the fraction line, you just negate the exponent? And then integrate. Now mu times q is just this times this. So we got minus 2x times e to the 4x dx. For those of you who haven't seen tic-tac-toe, your life is about to be changed forever. Because it's so right. It's good. So we have an exponential and a polynomial. And when you have this, you can take advantage of tic-tac-toe. So I'll just do it right here because it doesn't really need that much space. We don't really need that. So we always choose, the idea is, can we take one of these to be something that if you repeatedly differentiated it, it would just go away to 0? So does that work for an exponential function? Like if you were to repeatedly differentiate this, could you ever get it to equal 0? No. What about a polynomial? Yes, I love the energy. Energy I wish I had. Okay, so we make that equal to u. And then the dv is going to be e to the 4x. And so how this works is down this column we differentiate, and down this column we anti-differentiate. Okay? So what's the derivative of minus 2x? And then derivative of that. Yay, we made it to 0. Okay, so we stop. So then what's the antiderivative of this? And then if we were to anti-differentiate this, now we take this, march down 1, march down 1, start with pluses, and then we'd alternate plus minus. So if there happened to be more terms, we would just keep alternating plus minus. This is going to tell you the sign with which to multiply the linked pairs together. So this times this, a negative times a positive is a negative, so we'll have something negative. That 2 times that is just going to be 1/2. So we have x half e to the 4x is our first term. Now this, we're going to have a negative times a negative is a, right, so we're going to be adding our next term. What's the product between these that are connected? That 2 cancels with that 1/16, so it's 1/8. Do we agree? Okay.
Just run away.
And then we can, we got to make it look a little bit, well, we don't want to forget a constant of integration. Yeah, I'm almost really tempted to take out the half 2. So just 1/2 e to the 4x. And then this becomes. Wait, to get back to, so it'd be 1/4.
I understand why, like,
You know the right number.
I understand what we're doing, it's like, it's tic-tac-toe thing and everything that's happening, but why are we doing it? We're doing it to solve that.
Because otherwise solving this integral is a pain in the butt.
Okay.
Yeah, you could do it by integration by parts. It would just take you 15 minutes and that's not time you can afford. Yes.
Does tic-tac-toe method rely on eventually reaching 0?
Yes, if you, yeah, please don't, if you have like an exponential and a trig function, they're gonna go, blah, 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 you'll never get to 0. So don't. Oh, yes. This is how we know. Limit logarithmic functions, inverse trig functions, polynomials. So in this case, we had a polynomial. E is exponentials, which we have. So we had a PE. And T is trig functions. And the priority for you we choose U, which one is first. So L precedes I, which precedes B, precedes, etc. So if you had a log, so if you had like the integral of x times the natural log of x, you would actually have the log VU and then the PU. But that's Calc 2 stuff when we're reviewing the differential today.
What did I stand for?
Oh, inverse inverse trig functions, yeah. So
What did P stand for?
Wait, where's the line?
polynomial.
Oh, yeah.
Sorry.
No, you're good.
Like, I might remember.
I'm trying to think if it was nicer to take out the blank A.
By the way, if you get to a question on the test like this one that you didn't know how to do previously and probably won't learn in the next 2 minutes, write funny smiley faces and move on. And hope that you'll figure it out before the end of the test. Because this is, don't waste your time trying to learn something that you don't know.
Yeah, if you don't already know this,
Good luck.
good luck. Just leave it like this. I would, and then in this case, just leave it like this and then be done. If you genuinely don't remember how to integrate something like this, just let it sit, let it be, because this is as accurate as you're gonna get.
You'll get 3 to 5 points.
Right, you'll get credit, like especially in a Bernoulli, if you got all the way to here, you'd probably get 3 of those 5 points. Versus you could screw that up and waste time if you tried to do something. So all we gotta do is put this back in here. Note that I'm gonna put this big parentheses here. Because if you don't, it's wrong. So we have e to the 4x over 2 4th minus x plus c. Note that constant is a part of this. So it's inside of the parentheses. Please don't put the c out here. It'll break everyone's heart. Maybe not yours because you're the one who did it, but your grade, your GPA will thank you for just remembering little housekeeping details like that. See, because it's part of the integrand, it's a part of this integral. So this is really, that's set off in parentheses. Okay. So, did we find the answer?
That's equals y to the negative.
See, Mr. Euban's out here spitting not only memes and facts, but knowledge and wisdom. Okay, well, in that, I was not expecting that actually. Okay, so the Amogus has taught you well. So what do we do then though? Okay, so then, oh, y is 1.
Well, we just substitute on the problem.
So what was v originally?
It was y minus 2.
Cool. So all I gotta do is put equals blah, 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 and then you would just exponentiate it out. Yeah.
If you want it explicitly, then just.
Yeah, if you want it explicitly, then you would just this would multiply the exponents by -2. So I'll write the solution over here so that it's at least on the board somewhere, so you have it. It would be.
I thought this was, wasn't it, or the last one?
Easy is a relative word.
I don't find Bernoulli to be the easiest.
Linear, then it's easier to do early, but if not.
Separable is the easiest,
Yeah,
Unless it's really, really complicated.
then linear is.
this is just like hurting my head, like just looking at.
Oh, I have an idea.
Here's mine, it's
I
currently
mean, it makes sense, but
10
it's
o'clock
just,
at night.
I'm good.
Yeah.
I'm getting tired.
I'm just warming up the idea.
I need to drink water, honestly.
Well, that will actually conclude the recorded review. Yeah. I am actually just choosing to be too lazy to do an Euler's method problem on the recording because this recording is gonna nuke the storage on my computer.
Wait, are we reviewing whether it's forming on the test? 'Cause I don't
Yes.
think-
Yes, yeah.
There's gonna be a question.
Okay.
Oh,
I'm gonna
yeah,
finish
'cause there's one of
this.
those